also want to join my fellow speakers to Dr. China and also to for inviting me to speak here. So when China told me this, I was thinking, what should I talk about? Then I figured that since COVID already did the 3-day workshop on flatband, which I was not invited to talk about how to build flatband. Like already this morning, I worked with code elements, but theoretically, not experimentally. So one important approach in quantum simulation with code elements is a so-called bottom-up approach, which we design Hamiltonian that are interesting properties and try to realize this in code elements. I think that we want to motivate this audience that the flatbands are very interesting. So the natural question is, what are the models that support flatband? So this is I have to say that this is not a very new work. We did this work a couple or 3 years ago, but I think even interested in that community, for example, I think it's probably worthwhile revisiting this program, and I'll be very appreciative if you can give me some feedback on how to go further along the way. So I will first talk about some previous approach on building high-binding models that support flatband, and then I'll talk about our method, which I think is much easier and also more flexible. So if we have a block states, we can make superposition of block states to form localized wave-packet states, such as like the Wannier states. But in conventional lattice model, Wannier states, of course, not. They are superposition of block states, so they are not eigenstates of the Hamiltonian. But for flatbands, these localized states will be eigenstates because all the block states from the flatband we have the same energy. And we can build the so-called compact localized states. So these are the states that are most compact. So one way to so there is a way to generate flatbands from the compact localized states. So what you do is to you just choose some arbitrary localized states and assume that they are the CLS, the compact localized states. Then try to find out the parent Hamiltonian that gives eigenstates that lead these compact states to be eigenstates. So this is a very simple example I show here. Basically, you choose some compact states and use the idea of destructive interference to show that they are eigenstates of the Hamiltonian. So this is a simple 1D example that has in this program we can basically, so it's the inverse problem. You can find a parent Hamiltonian that supports that. But this approach has some challenges. It's not guaranteed that the inverse problem has it. And also, oftentimes, the inverse problem is quite difficult to solve. And particularly to go beyond the one dimension is quite a challenge. And also, in doing so, we can find the current Hamiltonian that supports flatband, but we do not know where in the spectrum range the flatband locates. And so this is the challenge that this approach will be facing. And so our approach is based on a very simple idea. It uses the so-called grand matrix in linear algebra. And so our approach, we do not assume prior knowledge about CLS, and we do need to solve any complicated math problems. and it can be applied to any spatial dimensions. And we also guarantee that the flat band will be viewed represent the lowest energy band. And for codec, it's quite important because the high energy bands are typically not very stable. So this is one of the features that we want this approach to have. All right, so let me first introduce graph matrix. You may or may not know this, but it's a simple idea in really everywhere. Say in some linear vector space, we pick some the dimension of the vector space is prime. Then we select arbitrarily some vectors and n of them, label them V1, V2, up to Vn. So the graph matrix is a conventional matrix, a square matrix. The elements are just the inner products of the vector. And another way to view these graph matrix is the following. So with these vectors, I write them as construct them as a column vector. So it's with n prime elements. So I align them to form a matrix called T. So this T matrix has a dimension of n prime times n. The graph matrix is nothing but a T dagger times T, which is n by n. So by construction, you can see that the graph matrix is a Fermat constant. Does not possess any negative eigenvalue. And furthermore, if these vectors, these n vectors that form the T matrix or graph matrix are linearly independent, we can show that the graph matrix is a positive definite. If that's not the case, if these vectors are linearly independent, then G is simply to possess at least one zero eigenvalue. And in fact, the number of zero eigenvalues is n minus the rank of the T matrix. And therefore, if the number of vectors you pick is larger than the dimension of the vector space, then Vi cannot be linearly independent. So you are guaranteed to have at least n minus n prime zero eigenvalues. And now you can see that how this is connect to flat bands. So if you think about this G as a Hamiltonian, then zero eigenvalue would be the lowest possible eigenvalue and you can possess. And in this way, a Hamiltonian that has a flat band. That's the ground state. So the idea is to construct this lattice model. You take some Hilbert space, and this R is the position of the unit cell space. And in each unit cell, I can have some a number of internal states, n internal states inside the unit cell. So this basically is a n band model. And so the dimension of the Hilbert space, of course, would be the small n, which is the number of cells times capital N. And how to build a Hamiltonian that possess flat band as the ground state. Now, in addition to the Hilbert space, we can also construct some auxiliary space. And this auxiliary space has the same unit cell structures as the Hilbert space, but the internal equilibrium is different. So in each in this auxiliary space, each unit cell possesses n prime internal states, and we require that capital N prime is smaller than capital N. Then we can make a mapping between the auxiliary space and the Hilbert space by constructing this T matrix. So when you apply T to a Hilbert space site, it is equal to so by construction you can equal to the right hand side. So the right side is the construct boundary of the space and with some arbitrary coefficients. And then your Hamiltonian is, as I said, it's just the T negative. And in this way, you are guaranteed to have capital minus capital prime bands with zero end. It's just guaranteed by the property of Riemann. So this is how you build flat band lattices, whose lowest bands are guaranteed to be flat. So this is the protocol. You construct a basis space in both the Hilbert space and the auxiliary space, and pick some arbitrary T matrix. And you can put in the impose the constraints on T matrix. For example, you want translation invariant, you want that the hopping is short range. All these can be so all these constraints can be imposed on this on T matrix. And then you just calculate what your Hamiltonian is. So there's no complicated math problem to solve. It's all by construction. So let me give a very simple example. Again, so 1D example, let's say that it's a two-band model. So each unit cell contains two sides, blue and red. And the auxiliary space should be smaller than the Hilbert space. So the auxiliary space, unit cell has each unit cell has just one step. And let me pick the T matrix in this one. And the corresponding Hamiltonian is given by this. So it corresponds to some hopping between the sides and contains hoppings within the unit cell and between sides from between adjacent unit cells. So these are the hopping amplitudes. And A and B are completely arbitrary. And you can show that the corresponding lattice is just the Kawasaki lattice, first proposed by Kawasaki in the context of theoretic. And this lattice has one flat band as the ground band. But using our approach, we can actually very easily generalize the Kawasaki lattice to arbitrary dimensions. For instance, if my Hilbert space has each unit cell has a d+1 internal states, it's a d+1 band model. And I pick my auxiliary space to have each unit cell contains d internal states. Then again, because d+1 is not given d, I'm guaranteed to have one flat band. Again, this is my T matrix, and the corresponding Hamiltonian looks like this. It looks like complicated, but it's really doesn't. It's not difficult to see. When I go in 1D, that's the example I just showed earlier, and this is the 2D example. Each unit cell contains three sides. And you are guaranteed to have the ground band to have the zero energy, to be flat, and this is the corresponding CLS for the flat band and for the ground band. And in fact, for this model, it's quite interesting. The top band is this is d+1 band model. The top band is dimension, and all the other bands are flat, so it contains d flat bands. And the middle bands, they all have the same energy. So d-1 of them, and they all have the same energy. And these middle bands being flat is guaranteed by the connectivity of this model. You decompose the whole size into subbands. You can show that the connectivity between the sides guarantees the middle bands to be also flat. So this is one example I want to show. And my second example is I call it the Kaplan-Meier lattice. Probably you haven't heard about that name, but it's just So in 2010, Eric Mueller and his at the time his student did an attempt wrote this paper, and what they want to do is to construct a parent Hamiltonian whose ground state are those nanostates but on the lattice set. And so this is the Hamiltonian we produce. And it's just a single particle Hawking between size j and k. And the Hawking amplitude is big J is given by this. So when I first read the paper, I asked myself how in the world do they construct this model with such complicated Hawking amplitude? Well, small t is just the sum of any scale intended to be 1, and GZ is on phase factor, and the Hawking amplitude has a Gaussian envelope, but it also has a complex phase. And because we want to construct a quantum Hall system, so the H field, this results in this complex amplitude copy. And you can show that given this Hamiltonian, the ground state are just in those level wave functions, and for arbitrary or degenerate. And in that paper, they didn't mention how they came up with this model. But now I suspect that they solved the inverse problem, starting from the wave function to construct the parent. But even for that, the inverse problem is not trivial to solve. Now, let me show you how we can actually come to this model without making any assumption. And for this, I need to say something about the coherence states. And what we first encounter coherence states in quantum mechanics when we study harmonic oscillators. In quantum optics, coherence states are also very important. We know that coherence states they're not energy eigenstates of harmonic oscillator, but they are eigenstates of an relation of A. So A being non-Hermitian, so the eigenvalue is not guaranteed to be real. So the eigenvalue Z is complex. And the coherence states possess a number of interesting properties. For example, no two coherence states are orthogonal to each other. So grab any two coherence states, the inner product is non-zero. And of course, the amplitude of the inner product decays as Gaussian between Z and Z prime. And the coherence states can also be used as a basis set, even though they are not orthogonal as a basis set. But unlike any eigenstates, the coherence states basis set is overcomplete. So there are more coherence states than we need to use as a basis. And coherence states are also often represented as using the complex plane. A point in the complex plane can represent a coherence state. So since the full set of coherence states are overcomplete, one question you can ask is it possible to select a subset of coherence states such that they form a complete but not overcomplete basis? It's quite a strange problem, but we found out that this problem was solved by a Russian physicist in the 1970s. He published the paper in some obscure journal, so it wasn't very well known. But the conclusion is this. I said that each coherence state can be represented as a point in the complex plane. So let's pick some points on the complex plane and assume that these points form a lattice. So here omega 1 and omega 2 are like the lattice basis vectors from which we can form a lattice. And just using the example, so the unit cell is the parallel graph. And the area of the unit cell is called S. And the conclusion is if S, the area of the unit cell, is larger than pi, then the corresponding set of coherent states are incomplete. And if the area S is less or equal to pi, the corresponding set of coherent states are over. In fact, if S exactly equal to pi, this set is overcompleted by just the one state. If you remove any arbitrary one, you have just a complete set. It's kind of weird, but that's true. So using this idea, we can actually construct our Hamiltonian. So my auxiliary space are just the coherent space, and my T is really simple. Just map the coherent space into my Hilbert space. So my Hilbert space represents the side and the particle can hop, particle can hopping. So my Hamiltonian is just like the matrix element of the Hamiltonian, just the inner product of coherent space. And so the Hamiltonian will have zero, will have eigenvalue 0 if S is less or equal to pi. Otherwise, if S is larger than pi, then all eigenvalues are positive. And the degeneracy of the eigenvalue 0 is given by this. It is 1 if S is pi, and equal to that if S is less than pi. Here, big N is the total number of states. So if your total number of states is macroscopic, so the degeneracy is also macroscopic. So the physical interpretation is the following. So it's a lattice model, and with the hopping strength decays as Gaussian, but it has a complex space. So it represents the gauge field, and the flux for unit cell is 2s. So it represents one whole system. And so this is one example. We consider a square lattice. So what I plot is the density of states as a function of the unit cell S. As mentioned that if S is less than pi, you have a flat band. You have a 0, the ground state energy is 0. And the exact state form is basically the Hawk butterfly. And furthermore, this flat band is very robust in the sense that it is independent of the lattice structure and create all kinds of lattice structures. And so this is the square lattice, the triangular lattice, this is honeycomb, and this one is the random lattice. It's not even a lattice, just the random points. So in this case, S should be regarded as some average spacing between sides. So the flat band is robust, independent of the geometry, and of course the butterfly pattern will be dependent on the exact lattice geometry. And so you can calculate the ground state, and universal again means independent of the geometry. And so it is the analog of the lowest analog. You can calculate the Chen number is 1 from 4 states. And also let me finally mention that how do you realize the flat band in these synthetic materials and do this using in photonic systems and also in atomic products. And in this particular example, we will construct the lead lattice and hyperbolic lattice have also been realized in the products. All right, so I think that's all I want to say. We developed a very simple method to construct a flat band with construct tight binding models that support flat bands. And these flat bands are guaranteed to be the lowest energy bands. And I can provide a couple of examples. One example is short-range hopping, but it's a non-topological system. And the second example is contains long-range hopping, but the hopping amplitude decay proportion and give to standard level states. It's a topological model. I spent my former student, who's my postdoc in Frankfurt,